So 6.3b, short, but there's a lot of meat to it because we are dealing now with repeated application of integration by parts. All right, so that's integrals within integrals. Okay, so a repeated application of how that's going to go. Now, yesterday, I introduced you to that acronym, LIPET, the Lipit test. But the advantage of every single one of the problems that I picked for you yesterday is that you had an L or an I or a P. And none of the questions I picked you with took you to that fourth option of E as your only choice. So everything at least had a log or an inverse or a polynomial. When you get to, if you've gone through all the options and you are on option number 4, which is an exponential, that is a dead giveaway that you're going to need a repeated application that's going to be done multiple times. All right, so here's how you know. What's the derivative of an exponential function? It's still an exponential function, right? And what's its derivative? Another exponential, and do you ever get out of that cycle? No. As different than like a polynomial, right? Because if a polynomial is like power 4, its derivative is power 3, and then eventually power 2, and then power 1, and then finally you get to a constant, and then you at least have gotten some, like you've gotten it all the way down. But an exponential just keeps being an exponential. And what about a trig, like sine? Its derivative is a different function, but it's still a trig function, and its derivative would still be a trig function, and you're like stuck in this never-ending loop. Okay, so then what do we, how do we handle that? All right, so that's our job for today. We ended yesterday with this question, which is the same question I want to start with. Okay, here is an example where we are dealing with a PE combination. So we have P, we have our polynomial, and we have E, which is our exponential. So kind of as in terms of a warm-up, I want to have us start with that. But it did require us to do it twice yesterday. So we pick our U to be 2x squared. Now, some of you, I was noticing, some of you do your derivative right away, and you do like 4x dx right away. And then you think about the remaining part, which was e to the x dx, and its antiderivative is e to the x. Some of you do it like in a different order. It's fine. It doesn't really matter. Okay. All right. So what we've got going on now is, and I always like to start with the question, and the question was 2x squared e to the x dx. It begins with the first part of the antiderivative solution was 2x squared ex, that combination. And then minus, and then the combination of 4x e to the x dx. And because we still have a p polynomial and an e, then we have to do it again because we still have that same combo. So now my polynomial choice is 4x, the derivative of which is 4 dx with the differential. And then e to the x being my v part and e to the x. And we saw that that combination led us to 4x e to the x as the first combination minus another integral of 4 e to the x dx. But that work that comes from the second time we've repeated that, what's essentially in front of all of that? Okay, that negative sign is in front of, I'll just use a big print, all of that. And what's in front of that is 2x squared e to the x. So it carries down. And so what I would want you to do first, so now we have an integral behind another integral, but behind a subtraction sign. And so I'd really want you to be real careful that you distribute that subtraction, that negative sign, so that it impacts it. So now I have a plus. And because 4 is no longer a polynomial, but 4 is a constant, then the antiderivative would be 4 e to the x. And then I have my plus constant c. And if I had bounds, the bounds would apply to all of that, okay? All three pieces that were produced by integration by parts. Okay, but it was that being behind the subtraction sign. So we saw this problem yesterday. Okay, any questions about that one again? Or you see it done twice? The fact that my first polynomial was what power? Squared. That's connected to the fact that I had to do it twice. Okay, so a polynomial that would be 3 or 4, it would be 3 times or 4 times. Eventually, that polynomial will get you all the way down to something that's a constant. You do it enough times. Okay, I wasn't like masochistic. I did not pick one that was like power 5 or anything like that. Yeah.
Only because, like,
repeated derivatives, because we keep picking the polynomial for the u, and every time we do, we take its derivative, and that helps us like lower the level.
and that's because the other one doesn't cancel out right away because e to the x
It's going to stay e to the x no matter what I do. E to the x is derivative is e to the x. Its antiderivative is e to the x. No matter what I do, that will still consistently be e to the x. Yeah. Okay. Now, here's an example that's putting it in a different category, I guess, more or less, because now you have no polynomial to start with. We're starting with, we have an e case. This is case number 4 or option number 4, and a trig case. And this is a unique situation because the exponential is going to stay an exponential no matter what I do to it, and the trig is going to stay a trig. It's going to change between sine and cosine, but it's going to stay a trig no matter what I do. And so I would be stuck in an endless cycle and never being able to get out. There is a way, though, so that's what I'm going to show you, how to get out of that. All right? So you still always want to pick, the e is going to beat the t, okay? Exponential beats trig. So e to the x is going to be your u, which means cosine of x dx will be your v. And then the derivative is still e to the x, so that's unchanged. And the derivative, excuse me, the antiderivative of cosine is positive sine. Okay, and we proceed like normal. This is where it's going to be important for you to write the problem down. You're going to see in just a minute why it's going to be important algebraically for you to have that there. So I have e to the x, cosine x dx is my original problem. And it is begun with what combination first? E to the x sine x. Okay, thanks. That's that first combination here, working myself this way. Behind that would come a subtraction, and it would become e to the x sine x dx. So now I'm still at an e and a t. Okay, so I do it again. All right, so we have e to the x chosen again, which is going to give me e to the x dx. And then sine x dx is the v part. And what's the antiderivative of sine x? Negative cosine of x. Okay, so this combination is going to produce for me negative e to the x cos x minus the integral. Okay, and then what happens in the next part? Okay, so what's the sign going to be? Right now, okay, it's minus e to the x, and then the next part would be a negative cosine, so that'll be a positive, and then dx. Okay, but what is in front of all of that? Okay, the negative sign that was preceding that work, and the e to the x sine x. And what was in front of that was the original e to the x cos x dx that I started with. All right, so distribute your negative sign back through all the parentheses. So we have e to the x cos x dx equals the first part, which is e to the x sine x, and then plus an e to the x cos x. And then what about at the very end? Minus, shoot, I am needing smaller. I'm gonna maybe just.
Mr. T.
Kick him off.
Like, how can you have a function equal to something minus itself? Because it's the same function.
Is he still on?
Yeah.
Ethan, run down there, run across the hall. I tried to kick him off.
What's the end of his eye?
Someone email him the code.
Ethan runs over goes 8085.
From both of them.
Okay. Oh, okay. And as soon as Ethan gets back, Isabella, I want you to ask your question using the exact words that you asked it. Okay, but I want Ethan to be in here to hear. Okay.
Just accept.
Yeah.
Just accept and move on. Because
All right, thank you. Okay, one more time.
How can you have a function equal to, like, two other functions minus the original function itself?
Itself. Okay, so you're seeing the original function itself again, right? Okay, because we end up with another e and a t combination, which is the exact same e and t combination we started with. Okay, what do you call two things that are the same as each other? Okay. Okay, another thing is we call them like terms, that these are like terms. Okay? All right, do those functions cancel each other out? Okay, because one of the functions is positive, but the other one is negative. Okay? But what if we move it to the other side, to be with, then how many of them are there? Yes, that is exactly correct. So, that's exactly what we do. So, two of these integrals must be equal to e to the sine of x plus e to the x cosine of x. Okay? Two of those integrals must be equal to that. Well, if two of those integrals are equal to that, then I only need to know what one of them is equal to. Okay? So we divide by 2. So e to the x cosine of x dx must be equal to e to the x sine of x, e to the x cosine of x. The whole thing divided by 2, and of course we have to remember, since this is an antiderivative after all, that it has a plus c on the end. Yeah.
You do all that work and then you
Okay, this is where the logic, the power of the logic of math, okay, can lead you to exactly how could something that is equal to two other things but minus itself, how does that work out? It wouldn't work if it was plus itself. That would be bad, because if it was plus itself, then we couldn't, if we tried to move it over, it would subtract and disappear. Yeah.
So right now it goes through 2 cycles and then it ends up at the same place.
Mm-hmm.
But if you like change the cosine of x so that it's not just cosine of x, it's like cosine of 3x or something, does that change the amount of cycles?
Okay, it does not change the amount of cycles, but it would change when you take your antiderivative. Okay, so that's a really good question. So suppose there was a cosine 3x here. Okay, then the antiderivative would be cosine of 3x, but what else would I have? I would have divided by 3, so I would have a coefficient of a 1/3 out in front, okay? So then I would end up with a 1/3 right here. Okay, having traced its way down. It would probably end up actually to be a 1/9. It would be a 1/3 in front of a 1/3. So then I'm not gonna, if I've got one of them over here and then minus 1/3 of them over here, when I combine them, I don't have two. How much would I have?
2/3?
No, one of them plus 1/3 more.
Oh, plus 4.
Yeah, because it's you're adding, you'd have to add the, okay, so then you'd have 4/3. And so then instead of just dividing by 2, you divide or multiply by 3/4. Yes, yes, yeah, yeah. Okay, yeah.
What if there was like a 2, it was the e to the x was like an e to the 2x or an e to the 3?
Okay, all right. Then we just have constants in front of the e term, which is fine. Okay, so then the antiderivative would be e to the 2x, but divided by 2, which means I'll just have a 1/2 in front of that one.
So it's like the same thing.
Yeah, yeah. Okay,
But the e to the 2x is cycling.
yeah, still keep cycling. You just get an extra bonus coefficient, okay, that just keeps going there. Yeah,
Can you go back to like it was cosine of 3x and y
Sure.
divided by 3?
sure. Okay. All right, if we want to find the antiderivative, this way. Okay, the antiderivative of that, okay. She's just doing a little bit of in her head. What's really going on is that 3x is being assigned to u, which means 3 dx is equal to du, which means dx is equal to 1/3 of du. So when we find the antiderivative, it'll be cosine of u times 1/3 of du, and the 1/3 gets pulled to the front. And so the answer would be plain y must be equal to 1/3 of whatever the antiderivative of the cosine of u is, which is the sine of u, plus c. And then you change the u back. So 1/3 the sine of 3x. So essentially, she's done that so many times now, she's remembering I can probably skip all of this stuff now if I just can remember that the antiderivative of cosine is sine, and the 3x means that I'm going to ultimately have a 1/3 or divide by 3 in the front.
Okay. Also,
Yep. So,
the little like chart thing.
yes.
Why is there never a plus c there?
Because that chart sign is just like scribble scrabble that we're using to just help us organize our thoughts.
Why not
Right.
Plug it in, there's no plus c either.
When you plug it in.
You have like multiple
Why is
plus
it
C
sine
and
of-
like
Oh, yeah, you do. I mean, they just keep combining with each other all the way. Sure, you want a plus C1 and then a plus C2 and then a plus C3 and then say, oh, they're all constants, so at the end, they're all going to be combined to one big old plus C at the end. It's true. That's the same. Yeah.
Like you don't know what the constant is.
Right. You don't know what the constant is. It is. They are there. I mean,
they turn into one.
they just keep, yeah, you just keep adding constant 1 and constant 2 and constant every time. I mean, the first time we did it, we only were doing it once, so we only had one constant. But if we keep repeating that, we will have multiple constants added together, which just combine into.
Are we gonna be asked, like, are we gonna be given something so that we can find the first constant and then we'll keep going and then we have to keep finding?
No, not, you just, if you have an initial, you're talking about initial condition, like, so no, then at the end, you would just take that one condition, plug it in at the very, you don't have to find constants as you go. You just find the one constant at the end. Yeah. Yeah.
So like, kind of like what we did here, we don't have to like write all the plus c's. Can we just add plus c to end?
Sure.
So just to say.
Yep. Yep. Yep.
Thank you.
It's got to be there somewhere, right? You know, so at least once.
Okay,
Yeah.
so we just have to then,
At the
we're
end.
not gonna like dock points off if we're not.
I'm not going to dock within the process, no. But at the end, like on the last test, some people forgot plus C, and that was, you know, it was, yeah. Okay.
Oh my.
All right. I was only going to show you one example. Okay. You are only going to be having this situation in an ET combination, right? This is the only time it happens is when you have an exponential. Like, it doesn't happen when you have a log. It doesn't happen when you have a polynomial. It doesn't happen when you have an inverse trig. It only happens in, you know, just think of the movie E.T., right? It only happens in this special ET combination. Okay?